I want to show you the power of a numerical calculation using Python. Okay, so let's start back with this. I have a ball, and it's just a normal ball. It's a bouncy ball. I'm going to toss it in the air. So we've done this problem. This is just normal projectile motion. It has a downward acceleration due to gravity of negative g in the y direction. Pretty easy to model. Here's another one. This is a ping pong ball. It's almost the same size, but this one has a mass of, let's say, 20 grams. This is 2 grams. And when I throw this up, it looks different. If I throw them up together at the same time, I can't catch them both. Oh, got it. Then they don't do the same thing. The motion of this ping pong is different. The motion of this ping pong is different because it has a downward gravitational force, but it has an air resistance force too. As it moves through the air, there's a backwards pushing force due to the interaction with the air. This one has the same force on it. However, since this has a much larger mass, that force doesn't really do too much to change the acceleration where it does with this one. So we want to model the motion of a ping pong ball that's tossed through the air. That's the goal. Okay, to do that, we're going to start with just a ball without air resistance. And we're going to solve this numerically by breaking it into small steps. Now, we do have to deal with some complicated things here because if we want to do two-dimensional motion, then we're going to have to deal with vectors. And we've done this before, but it's a little bit different notation. Okay, so here's my ball. I throw it. It has some initial velocity, v0, has a downward gravitational force, mg, and then the position of the ball I'm going to use as the vector r. So these are the vector g, the vector v, the vector r. They're all vectors. So the initial velocity I can write as a vector v0 cosine theta, where theta is the angle above the incline, v plus v0 sine theta y hat. So x hat, y hat, it's vector. I have an x component, I have a y component. I have a z component too, but it's 0. We're going to put the z in there in a second. The net force is just the downward gravitational force. So there's no net force in the x direction. I'm going to put 0 x hat and then minus mg y hat in the y direction. And then the position, I'll just say, is the initial position is x0 x hat plus y0 y hat. And instead of writing two kinematic equations, I can write just one kinematic equation. It looks like this. Instead of saying x is x naught plus vx naught t, and there's 0 acceleration, and y is y0 plus vy0 minus 1/2 gt squared, I combine that into this one vector equation. So this is the same thing. It's just as one equation, as a vector. And why do we care about that? Well, because we want to deal with things as vectors. The air resistance is a vector, and that's important. Okay. So, but we can model the motion of this using this equation because the acceleration is constant. But what if the acceleration is not constant? Well, then we have to cheat. So let's use this one. We know what it should do. Okay. So I'm going to calculate the net force on the object. That's it. And it's just mass times acceleration. And in this case, it's just mg. And that's the g vector. Remember, the g vector has a 0 x component and negative y component. But we would just say we add them up like that. And I can solve for the acceleration. The acceleration is f net. And notice I'm doing everything as a vector. So I can get the acceleration. If I break this into a short time interval, delta t of 0.01 seconds, then even if the acceleration is not constant, I can assume that it is. I can pretend that the acceleration is constant. If the acceleration is constant, I can write this. The acceleration is the change in velocity with respect to time. And these are all vectors, and that's fine. So that's going to be v2 minus v1 over delta t. So here I'm calling v1 the velocity at the beginning of the time interval, v2 the velocity at the end of the time interval. And I can use this to solve for the final velocity. So I'm going to multiply both sides by delta t and add v1, and I get this. v2 equals v1 plus a times the change in time, delta t. This is kind of a big deal. Because remember, I'm assuming the acceleration is constant over that time interval, even though it's not. But if the time interval is really small, it's pretty good approximation. Now I can make an even crazier approximation. I can assume that the velocity is constant, and I can write that as a change in r with respect to time. And again, notice we're dealing with these as vectors. That way we don't have to break it into x's and y's. And I can write this as r2 minus r1 over delta t. If I solve that for r2, I get this. r2 is r1 plus v delta t. This should be v average, and I'm not using v average. I'm actually going to use v2, the final velocity of that time interval. And then if I just write that over here, I won't write it. Okay, so here's my numerical recipe. Break it into short time intervals. During a short time interval, I'm going to calculate the net force and use that to calculate the acceleration as a vector. And then once I have that, I'm going to use that acceleration to update the velocity. And then I'm going to use that velocity to update the position. And then I'm technically going to do this. T2 is T1 plus delta T. I'm going to update time. That just moves to the next time interval. And then I'm going to do it all again. So I'm going to calculate this, calculate that, and that gives me 0.01 seconds. And then to get the next time, I need to do it all again. Nobody wants to do this hundreds of times, right? So we're going to have this do this in Python. So now one of the things that we're going to need, the very first velocity, I need to know. I need to know the first position. And then I can calculate the next one. If I don't know those first values, I can't calculate those. So let's go ahead and pick some values for everything. So I'm going to give it an initial velocity of 3 meters per second. I'm making up stuff at an angle theta of, let's say, 45 degrees. And I have a mass of, it's going to be a ping pong ball, but there's no air resistance, so it's in a vacuum. So a mass of 2 grams. And then my initial position will be 0 x hat plus 0 y hat. Why not start it there? Right? Okay. Let's switch to Python and make this happen. And I'm going to tell you as much as I can while we're doing this. Okay, this is Web VPython. It's Python with some built-in functions for graphing, has built-in vectors, it has 3D objects, but we're going to make this as simple as possible. But because we're going to add air resistance, I'm going to write everything as a vector. Okay, so let's just start writing our things. Well, I'm not going to write the mass as a vector because that's a scalar. So let's start writing down all our stuff. The first thing is g. I'm going to write g equals vector 0, negative 9.8, 0. So vector is a built-in class in Web VPython. I'm going to print that just so you can see what it looks like. And I'm going to run it. And so it expects 3 components because it wants to deal with 3-dimensional vectors. So it prints the x, y, and z components in this form, but it treats it as a vector. What if I want to add 2 to that? And I say g plus 2, what's going to happen? Well, nothing happened. And if you scroll down here, it says you can't add a vector and a scalar, right? So that's good. I keep looking at that camera, but it should be this camera. Okay. So you have to treat the vectors as vectors. I just want you to know that. Let's put the mass at 2 divided by 1,000 because that's the mass in kilograms. Now, I did not put my units here. If you want to put the units, you can put them as a comment. Newtons per kilogram, kilograms, okay, like that. And now let's put my initial velocity v0 as 3. Now, I wrote that as a scalar because I put it as a scalar up here. And then I'm going to have my angle theta equals 45 times pi divided by 180. What I just did there was convert it to radians because I'm going to need that in radians. My mass, my initial position, I'm just going to call this r. I'm going to write this as a vector 0, 0, 0. And again, that's in meters. Now I need time. The time step, let's use 0.01. Okay. Now let's just run this for 1 second. So I can do that with a while loop while t is less than 1. This seems like it's a little small Is that a little bit better? Make it bigger. Okay. While t is less than 1. So this says while the variable t is less than the number 1, then do everything that's tab indented after the colon. So you'll notice here that it already indented when I press return. So that's going to be all the stuff in the loop. When I dedent, I no longer indent it. It's no longer in the loop. Okay. So the first thing I want to do is to calculate the net force. I will say the F net is going to be m times g. Notice it's not negative mg, because this is going to be a vector. F net is a vector, and g is a vector. Yes, g has a negative y component, but this is a vector. So that's the way you want to add the forces. It's the sum of the forces. Now I can calculate the acceleration, F net divided by m. And now mass is a scalar, so you can divide a vector by a scalar, so that's fine. Next, I want to update the velocity, which I don't have. So let's make the velocity up here v equals vector v0 times cosine theta, comma v0 times sine theta, comma 0. So now I have my initial velocity is v, and I'm going to change that value. My initial position is r, and I'm going to change that value. So down here I can change that value. V equals v plus a times dt, and this is a make equal to equation. This is not a set equal to equation. It's not an algebraic equation. These v's do not cancel. Okay, so this just take the value of v, add a plus dt, and then make that the new value of v. So it updates the value of v. We don't have to worry about v1, v2, v3, and all that. It's just we're going to change the value of v. And the same thing over here. We're going to change the value of r. R equals r plus v times dt. And then finally, I want to update time. T equals t plus dt. If you don't put t equals t plus dt, your loop will go on forever because your time won't increase and it will never get to 1. So let's just print r equals, let's see if it even moves, r, and I'll give it units to meters. And I'm going to run it. Okay, so it went somewhere, right? Let's make a graph of the position as a function of the trajectory. So the x velocity, the x position versus the y position. So to make a graph in Web VPython, we're going to just give it a name, and it's going to be an object type graph. The title is going to be equal to, let's just say ball for now. X title is equal to x in meters. You can write whatever you want there. It's just a string. Y title is equal to y in meters. It's just a string. And then I'm going to give it width equals, since I have my thing zoomed in, width equals 400 pixels wide, and it will be a height of 200 pixels wide. You can put this whatever you want. You can leave it blank, and it'll give it a default size, but it might be too big. And then for the to plot thing, I need something called a G-curve. I'm going to give it the name F1. It's of object type G-curve. Color is blue. You can put whatever color you want. Now down here in my loop, what I'm going to do is plot a data point. F1.plot. Now, I want to plot the x position of the ball and the y position of the ball. So r is a vector. I can't plot r. I can get just the x component of the ball with r.x. That's the x component of a vector r. And then the y component would be r.y. Now let's run this and see if we get the trajectory that we expect. Yes, it is a parabola. This is the trajectory. This is the path in space. Okay. Now, it obviously went too far down, right? It went from 0 to 0, and it only took, that didn't take very long. I don't have the time here. So let's see, let's just throw it a little bit faster. Let's try 6 meters per second. Okay, that's better. So it is a parabola. Everything looks good. There's nothing new that we didn't expect there, right? But we have our program working. Now we can talk about adding air resistance to the problem. So let's go back to the board and add air resistance and model a ping pong ball. Okay, so what do we need to change? This is still going to stay the same. 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 I only need to change this first part right here, which is to calculate the force on the ball. So if I calculate the force on the ball with a different equation, then I can use everything else I already had. I don't have to change my code that much. So let's just talk about this other stuff that we're going to change. If I have an object moving through the air, then there's going to be a backwards pushing air resistance force. And we can model that as the textbook OpenStack Physics calls it the drag force, and it writes it like this: 1/2 rho A C V squared. So this is the number 1/2. This is the density of the air. So this has a value of 1.2 kilograms per cubic meter for air. A is the cross-sectional area, so that's going to be pi r squared, where that's because it looks like a circle, right? So we only care about that area right there, and r is the radius of the ball. C is a drag coefficient. For a sphere, I think it's 0.47. It's just a coefficient that depends on the shape of the object. I'm pretty sure that's true. We're going to leave it even if it's wrong. And then V is the velocity. But you'll notice the problem here. If I calculate this and add that in here as to my net force, if I just said, oh, calculate F drag and add F drag, there's going to be a problem. Vector, 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 not a vector, not a vector. Okay. So we're going to cheat. We're not going to write this in a vector. And my computer's freezing up. I don't want that to happen. Okay. Proceed, please. So I'm going to write this as a vector, negative vector. You can't square that, but I can take the magnitude. And then I'm going to multiply it by this thing called a unit vector. A unit vector is a vector in the direction of V. It has a magnitude 1, so it won't change all this. The negative means it's going to be in the opposite direction of that. I'm going to take the magnitude and square it, and then this whole thing is a scalar, and that makes it a vector. And then this becomes a vector, and I can add it in. So that's what we're going to do going back to Python. Hopefully Python doesn't skip like this one does. Okay, test. I think it's working now. Okay, I didn't want to start over. I'm already 17 minutes in. You can't go back now. So what we want to do here is to add in some parts of the drag force calculation. So I need my density, rho equals 1.2. I need my radius. I actually measured the diameter of the ball, and I got 3.5 centimeters. So it's going to be 0.035 divided by 2 for the radius. Oh, I can't use that. I got to use r, right? Because I'm using r, lowercase r, for position. And then I need a, which is going to be pi times r squared. Remember that in Python, squared is star star, raised to the power. Okay. And then I need my drag coefficient, 0.047. Okay. So down here in my loop, all I need to do to change this is to add in my air resistance force. So I'm going to type in the equation I had, negative 0.5 times rho times A times C times, now the magnitude of V. So we can find the magnitude of a vector with a function called mag. Mag V returns the magnitude of the vector. And then I need to square that. And then I need to multiply it by the unit vector. So there's a built-in function for the unit vector. It's called norm V. So right there, that's it. I'm done, right? Because I don't need to change anything else in there. Let's go ahead and run this and see what the heck happens. Okay. Is it any different? Did I have a mass? Okay, I can't even tell you the truth. So let's just make another object that's the same thing but does not have the drag force on it. I'm going to call it 2. So R2 equals vector 0, 0, 0. V2 equals the same thing right here. And then it has the same mass. So over here, I'm going to have an F net 2. It's going to be m times g. And then I'm going to have an A2. It's going to be equal to F net 2 divided by m. And now I'm going to update V2. V2 equals V2 plus A2 times dt, and then I need to update R2. R2 equals R2 plus V2 times dt. Now I want to plot that, so let's make another graph up here. I'm going to make a second graph called F2. F2 equals G curve, color equals color dot red, and then down here I'm going to plot that too. Sorry, getting out of control here. Okay, plot F2 dot plot R2 dot X, R2 dot Y. Let's see if there's a difference. No, there's not. Can't find FNet2. FNet2. Sorry. Easily fixed. Okay, good. So there is a difference, right? So here is the ball without air resistance. And you notice they're thrown at the same velocity. Here's the blue one with air resistance. So it's going to slow down. It's not going to get as high. And then on the way down, since it starts not as high, and it's already going slower, it's going to drop down faster. So this is not symmetrical. And you can really see the difference between those two when you compare it to one with no air resistance. So this problem is pretty much almost impossible to solve on paper. Okay, so you really have to break this down as a numerical calculation. So it shows you the power of a numerical calculation to be able to solve the kind of problems that wouldn't normally be solvable. And the code's not even that bad, right? I'm going to give you a link to this code. But, I mean, look, there's a lot of dumb stuff in there. I mean, 33 lines, and that's with 2 graphs, so not a big deal. And there you go. Hope you enjoyed that.